One of the things that we really wanted to do when we were planning this conference is to not just have theorists and philosophers and observationalists. We also wanted to have experimentalists and engineers. And so Dr. Unikrishnan is obviously one of our main experimentalists, but today we have a talk from Dr. Mike McCulloch, who's at the University of Plymouth, who is legitimately an engineer who is working on figuring out how to apply cosmological principles to actually being able to build propulsion systems. And so he has launched a test on a satellite into Earth's orbit and is trying to figure out how to actually get quantized inertia to be tested. And today he's going to be telling us about the science behind quantized inertia, how it works, and has the unbelievably unique perspective of taking cosmological principles and applying them to something very, very real and tangible. So, Dr. Mike McCulloch.
Let us see in the dark.
Well, thank you very much. So today I'm going to be talking about quantized inertia, which is a theory I've been suggesting for 20 years now. I think that physics has, in a sense, lost its way, mainstream physics, in that they're proposing things like curved spacetime and dark matter, which are things that cannot be directly tested. So what I'd like to do is to present a theory which can be directly tested. So instead of relying on curved space, things like that, to produce motion, it relies on variations in quantum background to produce motion induced by horizons. So I'll explain that as I go along. So I'll talk about the model of inertia I'm suggesting, which I think is the first one that's been suggested, first mechanistic one, give some evidence, astrophysical, talk a bit about a new cosmology based on it, and applications and lab tests as well. So inertia has always been a bit of a blind spot in physics. So many years ago, Aristotle believed that the default state of motion was to stay still, but we now know that this is rather ridiculous, because how do you stay still in a universe that's moving? How do you define stationary, as Einstein said? So the first change to this was Philoponus, who in the dying days of the Roman Empire, he proposed that maybe the default state was motion instead. Maybe things keep going in a straight line until you stop them. Then there were the Dark Ages, and that was largely forgotten, but Galileo in about 1600 came back, read Philoponus, and realized that this could allow the Earth to orbit the Sun, as Copernicus had said, without everything falling off the planet as it went. So he used Philoponus's model of inertia, and then Newton mathematized it. So this change to inertia took about 1,000 years to be accepted. So I'm going to argue for another change in the definition of inertial mass, which is quite fundamental, that the default state is not a constant speed, but is actually a minimum acceleration. So I'll try and convince you of that today. So I'm hoping this shift doesn't take 1,000 years to be accepted like the last one. And I'm hopeful, because this has its direct uses, as I'll try and show. So this, to try and illustrate the point, this minimum acceleration has a value of 2 times the speed of light squared divided by the cosmic scale. And this snail here is getting a bit worried, because it's a bit challenging for him, very slow moving. Okay, so I mentioned this analogy yesterday, but this is an analogy to what's going on. If you imagine a lake, so this is a lake, the surface of it, and this is an oceanographic analogy, because a lot of my background is in ocean physics and modeling waves, that kind of thing. Imagine there's a motorboat moving, accelerating to the right, and it'll see a lot of waves in front of it, because it's catching them up, and those waves will hit it from the front and push it back. But it won't see many waves from behind itself, because it's moving away from them. So the waves won't hit it as much. So in a sense, the boat will feel a pushback against whatever acceleration it has. And this looks a bit like inertia, doesn't it? And I'd like to introduce a little bit the concept of a horizon here, in that behind the boat, there's a bit like a horizon, which, due to the boat's own motion, there's a concept which is stopping the waves, some reason is stopping the waves from hitting it from behind. So this is a little bit like a horizon. And I'll explain this a bit more later on. But if we generalize this and we look at any object, so this black object here, accelerating to the right, then just like on the ocean or on the lake, there are waves. And in quantum mechanics, we know there are quantum waves all over the place. And Bill Unruh in 1976 predicted something called Unruh radiation, which is a kind of radiation you see whenever you accelerate. So this object is accelerating and it sees Unruh radiation, which is a bit like a thermal bath of radiation. And I've tried to show it with the red color here. Now this radiation has actually been seen by Lynch et al. In 2021. So it's not just a theory now. But also, because the object is accelerating to the right, there'll be part of the universe over here, which I've indicated as black, that it will never be able to receive any information from. So a bit like a black hole. It'll be a bit like a black hole for it. So there'll be a horizon there. And the new thing I'm suggesting is that this horizon damps the Unruh waves. So rather like the motorboat could not feel the waves from behind it, this object is not going to feel Unruh waves as much from behind it. So there'll be a push tending to push it back against whatever acceleration it had. And I managed to show in a paper back in 2013 that this predicts what we know is inertial mass mathematically. And just to prove to you that Unruh radiation has been seen, this is Lynch's data. What he did was, at CERN, he looked at positrons decelerating in a silicon crystal, and they emitted a radiation. And he managed to show that this radiation looked just like the expected spectrum for Unruh radiation. So this is the curve shows the predicted spectrum. This is frequency up here. This is intensity. And the dots show the data that they measured. So, and that's published in Physical Review D there. So Unruh radiation was confirmed, which was quite a relief for me, because I've been using it for 20 years. So, but it wouldn't be very impressive if I was just predicting something that's already been known, just inertial mass. There's a very slight difference. If the occupant of this motorboat was very smart, then he might work out that if he has a slow acceleration, if he accelerates very slowly, he could do so that the waves he makes and that bounce back off the sides of the lake are incredibly long because of very low energy. And if he accelerates slowly enough, then the waves would be longer than the lake. And then they wouldn't be able to exist. So it would be a bit like trying to play a note on a guitar where the wavelength of the string is longer than the guitar string. You can't do it. Similar to a lake. If the wave's longer than the lake, it can't exist. So that means that he would have no inertial mass in this analogy. So he would be able to move much faster. So that's a bit like... so it turns out that you can do this with a quantum vacuum as well. If you accelerate very slowly, this mechanism, so the mechanism I showed here, would not apply. Or maybe I should show you this one. Inertia is caused by the difference in waves on this side and this side. But if there are no waves, there's no inertia, because there's no difference. So we might be able to get rid of inertial mass, which would be quite useful. So I derived this formula, which quantifies this. So it turns out the way you have to do is you have to modify inertia. So this is the modified inertia. This is the original one. And it's modified by a factor shown here. So 1 minus 2 times the speed of light squared divided by the acceleration of the object divided by the cosmic diameter, which is a huge number, about 10 to the 26 meters. So normally this term is very small, so we don't see this effect in everyday life. It becomes significant if we reduce the acceleration, as I was saying. So if this A is extremely small, it boosts this term And that means that this factor is smaller, so the inertial mass becomes smaller. So that's how it works in the mathematics. In the theory, you can also make the effect more intense if you decrease the cosmic diameter. So that makes a good test, because I'm going to look at the early universe where the cosmic diameter was smaller. And I'm also going to apply it in the lab, where we can make a small universe in a cavity. Okay. So the great thing about this, for start, is that it solves the galaxy rotation problem. So this is the Andromeda Galaxy. Astronomers since 1980 have noticed that galaxies spin far too fast. So if you look at a star at the edge, it's orbiting around a galaxy, and it has a speed of about 200 kilometers per second, something like that, which produces a centrifugal force outwards, an inertial force. And it turns out that what they've seen in galaxies is that this force is far bigger than the gravitational force keeping the object bound to the galaxy, judging by the amount of visible matter we can see. So they tend to add dark matter to bind the stars at the edge to the center, because galaxies are obviously not flying apart. But what quantized inertia enables you to do, it predicts that the inertial mass of these edge stars, because they're accelerating so slowly, is reduced in a new way. So the centrifugal force is reduced by exactly the amount required to balance the gravitational force inwards. And it works perfectly, and there's no adjustment as well, because the theory only predicts one result, and it turns out that that result is correct, and I can't adjust it. All you need to predict stars is the visible mass of the galaxy, no dark matter, the speed of light, and the Hubble scale, which is now a known quantity. So I've published this in two papers shown here. So the first one, this is the first paper. So QI predicts that the velocity of the edge stars is given by 2g gravitational constant times the visible mass of the galaxy, speed of light squared, divided by the Hubble diameter. And if you look at the data, this shows various systems, galactic systems, so dwarf galaxies, spiral galaxies, clusters. This is the mass of the system. This is the rotation speed. And the data is the solid line, and the quantized inertia is a dashed line. And it agrees over this massive range of scales with these astrophysical systems. So that's this paper. And then I've also looked at some more recent data as well. That's shown in this paper. But perhaps the most conclusive evidence is that if you look at a galaxy spinning around, then in the center, the acceleration is very large. So the stars here will see Unruh waves that are quite short. So I've tried to illustrate that with these short waves here. So high acceleration means short Unruh waves. If you go out to larger radii in the galaxy, then the Unruh waves lengthen like this. But at exactly the radius of the galaxy, the acceleration is such that the Unruh waves are as long as the cosmic horizon. That's when quantized inertia predicts there should be a change, inertial mass will disappear, and that's exactly the radius at which all these galaxies start to deviate from Newton. So there's a smoking gun, if you like, in every single galaxy that we've ever seen, that this transition point is predicted by Unruh waves being as big as the cosmic horizon. So this is very solid evidence that this is the answer. This is the reason. Okay, I've also looked at wide binaries, which are stars which orbit very far apart. And the great thing about them is that they're orbiting far too fast again, just like galaxies. And the advantage with these systems is that you can't add dark matter to them to fix the problem. Because when they add dark matter to a galaxy, they have to give it new physics that spreads it out so it stays at the edge of the galaxy. So you can't then turn around and say, well, let's pack it into these small systems as well, because that's contradictory. So they can't use dark matter to fix these systems, but they're still spinning too fast. And it turns out that quantized inertia predicts these as well. So this is a plot. I published a paper with Jesus Lucio in 2019 testing this. this is the separation of the wide binaries. This is the speed of their orbit. The data is shown by these crosses, so they were averaged into bins. The uncertainty is shown by the envelope here, the gray envelope. Quantized inertia predicts this, so the theory also has an uncertainty here, so it agrees with the data. But Newton and Mond, which is a rival theory, do not agree at these wider separations. So, yeah. And then very recently, the James Webb Space Telescope has been discovering an awful lot of new things, and one of the new things is the so-called jumbos, Jupiter mass binary objects. So these are planets in deep space in the Orion Nebula that have the mass of Jupiter and orbit in pairs. So they have no star, they're just planets orbiting each other. So binary planets, which is a very new thing, and it's been published by Pearson and McCulloch. So yeah, they're quite widely separated, and the mass is about that of Jupiter, or a bit more. And quantized inertia predicts that there should be no acceleration below this 2 times 10 to the minus 10. So this is this 2c squared over the Hubble scale number. So I thought this would be great. This would be a great test. I'm going to look at these and see if any of them are accelerating less than this acceleration. So I did, and this is a plot here. So the separation in astronomical units is along the x-axis. And this is the mutual acceleration of them. And you can see that as they separate, as you look at widely separated ones, the acceleration does reduce, but they always stay, they don't go below this minimum acceleration at all. So if you might expect, if QI wasn't correct, that these would just decline in a linear line and go below the red line. And this is the minimum here. So in this case, quantized inertia also makes another prediction that these widely separated stars should have lost a bit of the inertial mass. So, and that means they should be orbiting slightly faster than we expect, a bit like galaxies and wide binaries. So I predict that for each separations of about 400 AU, they should be going a bit too fast by about 60, 70 meters per second. So I'm going to ask astronomers to have a look for this speed up. Okay. One of the advantages of this formula, as I said, is that you can, if you change the cosmic scale, it predicts a different variation in inertial mass. It predicts an enhanced effect. So the great way to do this is to look at the distant past, when the universe was informationally smaller. It's already used this, and therefore the inertial mass should be more affected. And there was a paper by Genzel et al. In 2017 where he looked at this and he plotted the observed accelerations against the predicted ones, and the redshift of these different galaxies is shown by these numbers. And you can see that as the redshift increases, as we look further into the past, the acceleration of these systems increases. And QI predicts this line here. And well, for these, it's not bad. This isn't a disagreement here. But I'm hoping that more of these systems will be studied so we can look at it in more detail. But generally, as the redshift increases, the acceleration increases as predicted. So I published that in 2017. And it's quite annoying as well, because just before Genzel published his paper in Nature, I wrote a paper predicting this and sent it to Nature, because I always send most of my papers to Nature at first, and then when it gets rejected, I send it somewhere else. And they rejected the prediction, but then about 3 months later, they published this paper with the observation in it. So, okay, so even further into the far past, the James Webb has just discovered what they call little red dots. So they look like this. They're obviously red, very redshifted. Their redshift is about 5, so they're very far off, very early galaxies. They found 341 of them so far, very early on, about 1 billion years after the Big Bang. But they're very small. They're very tightly packed, about 2% the size of the Milky Way, and they're spinning very fast. So the emission lines are very broadened. Rotation speeds of about 1,000 kilometers per second or more compared to the Milky Way, which is about 200. So they're small, fast spinning. So what does quantized inertia predict about these? So this is quite tentative at the moment, but I'm showing you this just to show what a kind of cosmology we might be able to make out of quantized inertia. So it predicts the velocity of the edge stars is given by this, as I said before. But also in quantized inertia, you can work out a value for g, and I'll talk about that in a minute. That g is c squared times the Hubble distance divided by the mass of the universe. So in this formula, you can replace g with these things. So that as the size of the universe decreases as you go into the past, g should decrease. But because mass is proportional to area, and I'll show you that in a minute as well, as you go into the past, the mass of the universe decreases even faster because it's proportional to area. So you would expect g to increase into the past because this is a more powerful factor. So that the velocity of the edge stars should be equal to the speed of light times the fourth root of the mass of the system divided by the mass of the universe. So I've put in some numbers. So if you look at the Milky Way, it's got a mass, something like that, 10 to the 41 kilograms. The mass of the universe is something like 10 to the 53, but that's quite uncertain. So you can see the error bar on the exponent there. There's a factor of 10 uncertainty in that. But that should improve with time and tighten up these predictions. So the predicted g is the one we know. The predicted speed is quite a wide range, but it agrees with the observed one. It's within the error bars. If we look at Genzel's 6 galaxies, they have a redshift of 2. Mass like this. The predicted mass of the universe is about 10 times smaller, because it was smaller then. The predicted g is rather larger. It's about 2 or 3 times larger. 3 times larger. So g was different. And the predicted velocity is, again, a very wide range, but it is consistent with the observed one. Then if we look at the little red dots, redshift of 5, much smaller universe, the predicted g is about 100 times larger. And it predicts these very large, quantized inertia predicts these very large spin rates of 1,000, observed about 1,000 or more. So it seems to be consistent. So as we can determine factors like the mass of the universe more accurately, we should be able to tighten these predictions up and see if it's correct. Because I'm trying to develop a cosmology here. I'm varying the Hubble distance, the Hubble scale, and the mass of the universe, but there's some indication that the speed of light might change as well. So, but this is great because this new data enables us to test this cosmology, which has not always been possible before. Okay, QI also predicts cosmic flatness. So the potential energy is roughly equal to the kinetic energy of the cosmos. The universe is mostly flat, as has been observed. Why is this? Is it a coincidence of the current epoch? This is very unlikely. But QI predicts this because in the theory, in any volume, the acceleration you have has to be large enough so that the Unruh waves seen are shorter than the size of the cosmos. So you can think of it a bit like the yin-yang symbol here. If you have a cosmos shown here, and there's a mass in it, this mass has to be big enough to produce accelerations so that the Unruh radiation is shorter than the cosmos. So if the mass was less, then these waves would be longer than the cosmos, and this would be philosophically bad because a horizon has to be a horizon. So a wave has to have a node on it a place where it's zero. If the wave went through the horizon, then the wave would enable you to see what was beyond the horizon. Well, to infer it anyway. So it wouldn't be a horizon then. So if you postulate a horizon, it has to be what I call a hard horizon. So this means that the gravitational acceleration has to be larger than this minimum acceleration. And then if you rearrange this, you get the potential energy is equal to the kinetic energy. And this is true at all epochs. So it doesn't have to be a coincidence of the present epoch. It's true for all time. Oh yes, and this is a bit I'm slightly ashamed of, but also puzzled by. So forgive me in advance. If you take this equation here and you write out the universe mass here, so 2c squared over g times the Hubble distance, Hubble scale times radius squared, then it turns out that this, if you put the numbers in here, you get pi, which, I mean, I'm a trained physicist, and this is not a dimensionless number. There are dimensions to it. So I shouldn't be saying this, but yeah, I'm ashamed of myself, really. But this is pi, and this kind of makes sense because in black holes, mass is proportional to area. Also makes sense in quantized inertia, because in quantized inertia, mass is determined by an area, which is a horizon, which is flat, is an area. And also Dirac. Dirac had his large numbers hypothesis, in which he showed that if you take the mass of the universe divided by the mass of the proton, then it's the square of the radius of the universe divided by the radius of the proton. And he never understood why, but it was just interesting. Well, this predicts why it should be if mass is area, equals area. So anyway, this explains flatness. It gets rid of the need for inflation or early fine-tuning of the cosmos. Gets rid of the need for special era now, because this is always true. Okay, you can also get the value of g, as I've alluded to. So taking this formula derived from quantized inertia, you can rearrange it for g. So g is the speed of light squared times the Hubble scale divided by 2 times the mass of the universe. Now this actual relation has been guessed at or known for many decades. People have noticed that this is roughly true. Dirac, Sciama, and I'd recommend you read Unziger's Einstein's Lost Key, because he talks about this a lot in there. So QI gives a Machian reason for it. The reason is that mass must exist to ensure that Unruh waves are short enough to be observable in the universe. It's kind of a philosophical reason for it. But it explains G. So this means that we can get rid of G in physics. Not quite yet, because we don't exactly know the value of the mass of the universe, or there's a 10% error in the scale of the universe that we know. But as this is tightened up, we can replace G. And this is interesting because it means that G isn't just a constant. It's got things in it which change with time. So it should change as the universe changes in mass and size. And that can be tested for and predicted. And it may also be controllable, because if we make an informationally closed space, for example, we might be able to change G within it. But that's more speculative. Okay, so if we can unpack G, it becomes perhaps controllable. Okay, so there are several predictions here that you could look at later, I guess, but there are several interesting things. For example, QI predicts that inertial mass should reduce along spin axes. So any object that's spinning, the inertial mass of a body near to it must be lower near the axis. And this predicts certain things like the flyby anomalies, for example. But it might also explain galactic jets, and maybe also the bullet cluster, which looks to me as if the anomaly is along the spin axis of the system. But I haven't looked at that in detail yet. It needs to be modeled. Okay, so now I'm going to try and bring this cosmology into the lab. So I was doing a write in astrophysics but it was quite theoretical. So I started writing papers applying this to anomalies from the lab. So there was something noticed by Roger Scheuer in the UK, who is an engineer, and what he did was he had a asymmetrical cavity, and he had a magnetron in there. He put microwaves in, and he found that it moved slightly towards the narrow end. And this is extremely controversial, and it was only a very slight thrust as well. But I found I could predict it with quantized inertia, because at the wide end of the cavity, more Unruh waves are allowed, because there's more space. At the narrow end, fewer Unruh waves are allowed. So inertial mass can be larger at this end and smaller at that one. So if you have electrons in the walls, or microwaves shuttling backwards and forwards, then every time they go this way, they gain inertial mass, and every time they go that way, they lose it. So to conserve momentum for the whole system, the cavity has to move towards its narrow end. And I found that I could predict his results almost exactly. So I wrote a paper on that here. These were called the M drives. It's a very controversial observation, of course. And then I was contacted by DARPA, which is the US Defense Advanced Research Projects Agency, who asked me to test this in the lab. So I applied for funding, and I got $1.3 million to do it. So they asked me to demonstrate scalable thrust in the lab. So we started doing that, and then two engineers, Becker and Batt, suggested, why don't you try, instead of a cavity, why don't you try a capacitor? So I had a look at capacitors, and yeah, this was a very good idea, because with a capacitor, you have two metal plates, of course, very close together, and the accelerations are extremely large, 10 to the 19 meters per second. So you would expect a lot of Unruh waves outside, fewer Unruh waves between, because these waves don't fit. It's a bit like the Casimir effect. So this means that more inertial mass outside, less inside. So an electron crossing the gap will lose its inertial mass. So to conserve momentum, the theory is that it will move towards the anode, towards the direction the electrons are moving. So I looked at this theoretically and predicted that this should happen, and it agrees with the observations that Becker and Batt found in their lab. So they worked in the lab, and I worked on the theory part. And this is the result. So the separation of the plates is shown here on the x-axis, and the force seen is up here. So this is about 6 millinewtons here. The observations are the black diamonds, and the prediction is are the squares. And they agree within the error bars in all cases. So I published a theory and the comparison with their experimental results here in this paper, 2021. And their experimental method is published in this paper, Becker and Batt's experiment. So other people then became interested, and we did an experiment at Plymouth as well. There was an earlier capacitor test by Honda, actually, in 2008. And they had to predict, they had an observed thrust of 14.5 millinewtons, and I predict 14 for that. That's in a paper in Journal of the British Interplanetary Society. Becker and Batt, they saw 6 millinewtons, and I predict 5.7. Their papers on the archive. And then an American company called Ivo got involved, and they tested Becker and Batt's results in a proper vacuum chamber in Virginia somewhere. And they got 6 millinewtons from the capacitor, and I predict 5.25. So these are all in agreement with the data. And then we tried at Plymouth, and we saw a much lower thrust, but still it was equal to the one predicted, 0.25, 0.25. There was a beautiful experiment done in Italy, actually. They did it beautifully by depositing all sorts of things on capacitors and having a vacuum chamber. And they also agree with the theory. An ex-NASA engineer called Charles Bueller did a test, which is slightly different, but very similar to a capacitor. And we also agree. Group in California, Barnhart-Weed. And then Ivo Limited, this company here, decided to send a test into space on satellite. And that's been launched. They've actually sent 2 up. They sent one last year up into space, but they lost contact with the satellite before they could do the test, before they could switch the capacitor on. They sent up another one in March this year, so we're waiting for it to be switched on. But the predicted thrust from that is about 1.75 millinewtons, so they're hoping to raise the orbit by a few kilometers, which would prove that the drive is working. The Ivo have also, as I said, tested their drives in a very good vacuum, and they're very confident about the thrust that they've got. So we're waiting for the space results. So if you want to track it, it's got a NORAD number of 63235. You can. I'm following it every day. This is what it's doing. So this is the height of it in kilometers, 514 kilometers. It's at the moment it's falling, as you'd expect, but we're hoping it'll be switched on soon. And then we'll see. So it was a SpaceX launched from a Falcon 9. The actual satellite is a Rogue Space Systems satellite. So they're hosting the drive. There are 2 of them actually, one at this end, one at this end, and they're pushing in this direction. This is what the satellite looks like. And this is the Ivo chief executive, Richard Mansell, who has who decided to test this. So I'm very grateful to him. So yeah, it's okay. So lots of things to do with quantized inertia. So I'd like to see whether QI predicts lensing in a bullet cluster. It seems to, but I need to do a proper study of that. Where does the energy come from? Well, I can show you a derivation. The energy for inertial mass seems to come from the information that's deleted when these horizons form. It agrees exactly. I can predict it. I can show you the derivation as well. It's an exact prediction. Can QI predict particle masses? I'd like to try that. I'd like to. There are certain indications that the thrust can be hugely enhanced, so I'd like to look at that. Obviously, I'd like to help more generate more lab space tests. I think energy can be extracted from QI because, in a similar way to the capacitor thruster. And I'd like to look at more of the details of Unruh horizon interaction, because this is a very new part of physics. Unruh radiation has only just been seen, and horizons have only just been started to be used. So, and a comprehensive mathematical formulation needs to be undertaken as well. Okay, so to conclude, so quantized inertia is more intuitive, I think. Testable explanation for inertial mass. I've been suggesting this for 20 years, publishing papers. I've got about 27 now. It's got lots of proof: galaxy rotation, wide binaries, lab thrust tests on all sorts of scales. It implies that inertia is not a thing a body has within it. It's more like an interaction between it and everything else, which is of course very Machian. It's simpler than general relativity, and it does the same job. There's no gravitational constant that gets rid of that, so Alexander should be pleased about that, I hope. Predicts flatness, and I think it's more predictive in time and in the lab than other cosmologies. You can actually use it in the lab. There's lots of work still to do, but yeah, the aim is to make a testable, predictive, simpler, and more useful physics. So yeah, thanks for listening, and please buy my books. Well, this is the most recent one, Quantized Accelerations. And if you have questions, ask them now or email me here. Oh, and if you can follow me at Patreon, that'd be great as well, because I write a couple of articles a week. So thanks very much.
Very interesting, because you have a very clear mechanism for inertia and very clear predictions. Now I want to make 2 comments. One is on the theoretical backing of this. So since it is Unruh radiation, we are talking about the quantum vacuum of known interactions generating the Unruh radiation. That's electromagnetism and gravity long range, because you need the radiation extending over the size of the universe. So it is, if it is electromagnetic vacuum, then you are talking about electromagnetic push due to these Unruh waves.
Yes.
Which means, which seems to me that it will be different for charged particles and uncharged particles, which is a concern, but one has to think about it. Whereas if it is quantum vacuum of gravity, it is universal. It will affect everything equally. So that's just a comment on the theoretical part. The second comment is an experimental test, which is more interesting to me. I remember a discussion I had with Milgram 3 decades ago for testing MOND in the laboratory. And then it turned out that MOND is not testable in the laboratory because of a nonlinear theory, local gravity matters, and so on. But the test I was trying to do was, it involved a torsion balance, which we were operating at that time, torsion balance to test equivalence principle. And our balance had an acceleration well below 10 minus 12 meter per second square. So, but it existed in the lab, something with the acceleration less than 10 minus 12 meter per second square, which is smaller than the minimum acceleration you mentioned here. So I will think about it more, but my feeling is that there are systems, operating instruments where the acceleration is smaller than that. Also, there is a microscope experiment which was sent up in space several years ago to test the equivalence principle. There, the acceleration of those masses is of the order of 10 minus 14 meter per second square.
Yeah,
Okay,
I can answer that because if these torsion balance experiments are a bit like Galileo dropping his 2 balls off the Tower of Pisa. It's analogous to that. So quantized inertia still predicts that the 2 balls will fall at the same time because the modification of inertial mass is independent of the mass. So QI will not turn up in torsion balance experiments. It won't be seen in them.
Torsion balance itself as a system, accelerated system mass, it has an acceleration while it is operating, which is smaller than 10 minus 12 meter per second square, which is smaller than the minimum acceleration you mentioned.
Yeah, I understand. Yeah.
Thanks, Mike, for the beautiful presentation. It's not a question. I have to warn you, it's not a question, it's a comment, and I think one that you will like. When you go to this very weird result that you have the mass equalized to the area, I had to think about Sergio, who Sergio told me yesterday. It's with such anomalies that we typically have perhaps a breakthrough or something of a breakthrough hiding in there. And I want just to mention here that Mike's theory seems to agree here somewhat with a theory here from someone in the audience. Very weirdly, I think many of us have this intuition, have this suspicion that the electromagnetic force seems to have something in common of an origin with gravity, that they both belong to the same, whatever it is, force or something else interaction. So mass equalized to area should also somehow include the charge equalized to area. Michael Gunning, in his model, based on just a couple of springs, basically trying to model mass and matter in that way, comes to his conclusion, like, oh, I have to equalize Coulomb with meters squared. Curious.
Okay. Yeah, we can talk about that. Yeah.
First of all, I'd like to say this was a really great talk, and I really enjoyed it. I have two kind of related questions. So, first of all, I wanted to ask, as a cosmologist, if you have any prediction for the expansion rate history of the universe?
Well, at the moment, I'm assuming it's expanding at a constant speed of light.
So the A
But-
is proportional to T, kind of
Yes.
model. Okay.
So, but I'm not entirely sure about that.
Okay. Yeah, that's fair enough. This looks like a theory for relatively small scale systems, down to even the lab. What I wanted to ask is, so this might be a bit difficult to answer without a good understanding of the cosmology, but it seems like you predict the gravitational constant G to vary with time.
Yes.
Is that right?
That's right.
Okay, and how would it vary with time? So it would be higher in the past?
Yes, higher in the
That's right,
past,
isn't it?
linearly with time,
Okay.
with redshift.
Oh, so G proportional to 1 plus Z.
Yes,
if
so
I
I
understand.
showed some values of G. So this is redshift, and this is the predicted value of G.
Oh, so this is like triple the current value,
Yeah,
and this is
100,
okay.
well,
This is not, yeah. Well,
30 times.
Okay, this is a slightly more than 6 times the present value then. Oh, but
Yeah,
anyway,
it's-
the main thing is the reason why I wanted to ask is because I mean, I'm guessing in this model the mass of the sun would not have changed over its 5 billion year history.
Well, I wouldn't go so far as to guess the sun's evolution, because there are lots of processes determining stellar evolution.
Sure.
So this is on top of whatever else is going on.
Yeah, naturally. No, the reason I want to ask is because of constraints from like helioseismology on the evolution of the sun. Because there's a very good match between the age of the oldest meteorites using like radioactive dating and the age of the sun from helioseismology, but with significantly higher G in the past, or even actually relatively slightly higher G in the past. What happens? The nuclear reactions in the sun would be much faster when G was higher, and that may lead to a mismatch between the helioseismic age of the sun and the meteorite age. So that's just something to
Okay,
consider.
that's interesting.
Yeah,
Yes.
I have a paper called like challenges to a change in G as a solution to the Hubble tension, because people have proposed changes in G for various reasons. Here, of course, it's not something you wanted to happen. It's just a natural consequence of the theory. That's what I wanted to mention.
Okay, thanks.
Thanks. Very interesting theory, and thank you for the talk. And my question is, inertia is a sort of reaction to an instantaneous force, effectively. You know, if I hit this tape, it moves immediately.
Yeah.
So my question is, how does that Unruh wave, which I can understand the experiment at CERN is a very local thing, and you can sort of probably see where horizons and edges of test cells are. How does it instantaneously interact with this distant horizon? Is there a propagation speed of the Unruh wave through the distant universe? Is it instantaneous?
Well, I have several possible answers. The first one is that this only seems to work at the Planck scale. So in my paper in 2013, when I derived the formulae, it only works when you consider the Planck scale. So that's that's in the realm of quantum mechanics. And with things like EPR, communication can be instantaneous with that. Also, in Einstein's relativity, there's no preclusion for monochromatic waves to move faster than light, because they're not directly carrying information.
So you are imagining an instantaneous
Yes.
interaction with,
Yes.
with the distant universe?
Yes, I am.
So Mach's principle is in here somewhere, I guess.
Yes.
Okay, that's it. Now, if just final quickie, the model, I presume, is entirely dependent on a Big Bang cosmology of finite size, though. If we do sort of ever get to a point where we think the universe was infinite, would this be relevant? Or could it be modified to such a change?
Well, it's different to the Big Bang because I have no direct proof of this, but from the theory, I think that we have more of a steady state. But the informational sphere, Alexander was mentioning this yesterday, that the informational sphere is expanding. So for every new piece of matter, as soon as it's formed, the informational sphere grows with time.
But that has a speed of light delay in it.
Yes.
And we've just said but you've said instantaneity has something to do with it. So that could go beyond the information sphere.
Yes. Okay, that may not be exactly consistent, but what I'm saying is that the universe is not expanding, but the informational horizon that we all have is. So
okay, we can explore. Thank you.
Thank you so much. Thank you, Dr. McCulloch. Round of applause.